Welcome back, guys. We're halfway done. We have two more sets of FRQs to go for this year's Physics C exams, and then we're all good. Now it's time for both of the E and M sets, right? We're going to do set one in this video, set two in the next one. And I actually kind of found these to be mostly easier than the mechanics ones. It was kind of weird, but that's kind of how I feel with E and M ones, just because there's fewer units, and it's a little bit easier to kind of piece together some sort of things to take a look at too. But let's just go ahead and get started. So we have two spheres, right? Sphere one is attached to an insulating rod, and then sphere two is hanging from a string of negligible mass as well. Right, sphere one is brought near without touching sphere two, and we have equilibrium. Right. So if we go on to the next page when the question actually starts, and College Board really loves to do that nowadays, which is fine. It's I'm really glad that they're setting up the problem so well. Right, we get to the first question, which asks us, right, to draw a free body diagram on sphere two. Now, sphere two is the one that is hanging on the string, so we should expect to have tension force. Right, tension force is going to point at an angle, right, with theta being right here. We don't have to actually label theta, so we can go ahead and get rid of that part, right? And then we also have gravitational force pointing down, as well as electrostatic force pointing to the right due to repulsion. Now, keep in mind that the electrostatic force should match the horizontal component of tension, and the vertical component of tension should match the weight force. This is an equilibrium problem. All right, part B says to derive an expression between distance and angle to show that, and then we're given the actual equation we're trying to find, which is good because we're going to need it for the rest of the problem. And in terms of this, we just drew a free body diagram, so you can probably guess that we're going to be using Newton's second law equations, right? Sum of all x components of forces is zero, likewise with the y components. Now, in this case, it's actually going to equal the x component of tension is ft sine theta, not cosine, right? If you go back to the picture on the previous slide, you're going to see that theta is the angle from the vertical, not the horizontal. So that is a negative force because it's pointing to the left, although it doesn't really matter which way is negative and positive here, plus the electrostatic force, that should all equal zero. So we know that that's going to be negative ft sine theta. Plus, and the electrostatic force is 1 over 4 pi epsilon naught times the product of charges over the distance between those charges, d squared. Now, the y components of forces, Fd cos theta, is going to be minus mg, which is the weight force, is going to equal zero. From that, right, we don't have tension in our final expression, so let's go ahead and try to eliminate that by substituting, right? So mg over cos theta is going to equal tension. Plugging that into our equation for the horizontal components of forces, right, we get negative mg tan theta, or mg, or if we just move the negative stuff over to the other side with the zero, we can say mg tan theta is equal to 1 over 4 pi epsilon naught qq over d squared. Right, solving that for d does yield the equation written above. I'm actually not going to go ahead and rewrite it. I'm just going to put a check mark there. We got it. Obviously, you would want to go ahead and just rewrite it in your final solution. Again, I apologize for my tablet setup. I know that's kind of laggy and not the best in terms of lines, but hopefully it's not really detracting too much from your understanding of the video. Good. So in part C, right, the values that are collected are shown, and we're trying to calculate the force of tension. Well, we're given charges, we're given distance and angle, so let's maybe go ahead and use the x component of forces where we have all of the electrostatic quantities. We can say from there that Ft is going to equal 1 over 4 pi epsilon naught. Remember that epsilon naught is on our equation sheet. Times the product of charges over d squared sine theta. Now we're given all of those quantities. We can go ahead and plug them in. Note that both charges are the same, so we would just square 6 times 10 to the negative 8th on the top. Make sure your calculator's in degrees to get sine of 12 degrees correct, and then 0.057 meters squared. Epsilon naught is 8.85 times 10 to the negative 12th. But what that ends up working out to be is 0.05 newtons. Good. Next page, another best fit line, right? There's always a best fit line question. So you can go ahead and draw it. And as you might expect with basically every single time that we have a best fit line in physics C, you're going to have to take the slope. Right, so let's just go ahead and do that. The slope itself, I calculated from my best fit line, which I'm not going to go ahead and try to draw here. I could estimate it, but it's going to be different than what I actually had on paper. I got that the slope was going to be 7.7 times 10 to the negative fourth power. Now, the points that I used for that, if you want to try to draw out your own best fit line and check, I used 2, 0.001. So that's the point right about there where where I'm drawing a little bit. Hopefully you can see that. And then for the second point, I used 6.5 and 0.0045, which is approximately right here. Again, everybody's best fit line is going to be slightly different, including 2 best fit lines that I draw. That's why I'm not going to draw another best fit line. But just as usual, do not make sure that you don't include 0, 0 unless your best fit line happens to fall through there. Right, and when you're calculating the slope, do not use the provided 5 data points unless 2 of them are already on your line, right? Then you can use them. Good. So using the best fit line, find an experimental value for epsilon naught. That's not too bad because if we take our equation from part B, right, what we actually find is that d squared over 1 over tan theta, which happens to be what we're plotting here, that's going to be our slope now, right? And in terms of our equation, what that's going to actually equal will be the product of charges divided by let's see, 4 pi epsilon naught mg. So we can solve that now for epsilon naught because we also know the mass, right? So that means that epsilon naught should equal the product of charges divided by 4 pi mg times the slope. I actually kind of like these slope questions. I don't know about you guys, but I do actually find them quite fun, although a little bit tedious with using the data points. What I ended up actually getting was epsilon naught is equal to 7.44 times 10 to the negative 12th, which if I'm approximating, probably about like a 12, 13-ish% error. Again, I haven't actually done that calculation. We're not asked to do that. But yeah. And in terms of the units for this, you are given the units for epsilon naught on your equation sheet. I don't think it's really worth trying to work them out via dimensional analysis because it should end up being the same thing on your equation sheet. So just copy those units down from there. I used Google to help me out because I didn't have my equation sheet handy. It's something like this. You could also represent it in terms of things like newtons and coulombs. I think that's how it's represented on your equation sheet. But the important thing is to make sure you have units there. So good. All right, let's go ahead and move on. We're still on question number 1, but we just have one more page left with that. So let's go ahead and take a look. We do, on this next page, take sphere number 1 and replace it with a conducting sphere 3 with the same size and charge. And now what we're expected to do is draw a single positive charge where there's high concentration of them on sphere 3. That should be on the left side. And the reason why it should be on the left side is because the sphere is conducting, meaning that the positive charges will repel. The positive charges on sphere 3 will repel from sphere 2. Therefore, and I'll move the text box in a minute so you guys can read the full things, but therefore they concentrate on the left side farther from sphere 2. Right, and therefore you could expect that the negative charges will concentrate on the right side, closer to sphere 2. All right, there you go. Now, in the original experiment, right, theta 1 is the angle from the vertical. In the modified, we're asked about theta 2. Now, this is the one part I'm not 100% sure of, but my physical intuition is telling me that theta 2 in the new experiment should be less than theta 1. And here's my justification for it. Again, if you disagree with me, or even if you agree with me, right, feel free to let me know. It's always nice to have another set of eyes. Again, College Board doesn't release their solutions until later this year. So right now, these are just my solutions, right? There could very well be an error. I'm not perfect with physics. despite having studied it for years, right? I still make some mistakes sometimes, but that's part of being a scientist. All right, my reasoning for why theta 2 is less, is because the positive charges repel and the negative charge on sphere 3 will attract to sphere 2. On average, the negative charges on sphere 3 are closer to sphere 2 than they are in the first case, right? And likewise, the positive charges are farther away on average. Therefore, we expect the overall electrostatic force, as usual. I will go ahead and move the box in a minute. I realize I'm running out of space here, so you won't be able to see the full thing, but we do expect the overall electrostatic force to be less repulsive in trial 2 because of that distance. So there will be less deflection. All right, there you go. Hopefully that makes sense. Yeah, lower electrostatic force, less deflection, because now the tension doesn't have to be, the string's not going to have to deflect as much, and give you a larger tension force overall. Good. That's it for question number 1. So I'm going to go ahead and clear this just so we have a clean slate for question 2 here. Question 2 says that we have, it's a very complicated situation, right? Bar is compressing the spring. At time t is equal to 0, the bar is released from rest and pushed to the right. T is equal to 1, the bar loses contact with the spring. T is equal to 2, it enters the first field section. T3, it enters the second field section. T4, it leaves the magnetic field. All right, consider the time T2 less than TB less than T3, and to draw an arrow for the net force. I claim it's going to be to the left. I claim that there has to be a net force here. Why? Because there's an induced current. This is a Faraday's law question. It's very similar to something like a simplified railgun problem, or I guess a more complicated one if you take into account that there's a spring. But what's going to happen is, as this bar is moving to the right, which it is doing between T2, T3, it is going to actually get an induced current because there's more flux pointing into the page. What the right-hand rule says is that as time goes on, if more flux points into the page, that means that the induced current has to be counterclockwise, right? That has to be the induced current in this loop, given by the bar, the two rails, and the resistor. So if the induced current is counterclockwise, it's going up through the actual moving bar. And in that case, the right-hand rule would actually tell us that with field pointing into the page, the magnetic force due to the Lorentz law is going to be pointed to the left. So therefore, net force should be pointed to the left. All right, let's go ahead and move on to the next page. I'm pretty confident with that one. Good. So if we do go ahead and take a look at this next part, it asks us to find the magnitude of the current given a value of velocity. And that might seem difficult, but if we're trying to find current, keep in mind it's induced. Therefore, what we should expect is that current is equal to induced voltage over resistance. As I mentioned before, we can get induced voltage via Faraday's law. Now we're just asked about the magnitude, so I'm just going to take magnitude of d phi dt from Faraday's law. Now what's changing here? Well, the magnetic field is constant, and we know that flux is going to be equal to, in this case, just B times the area of the loop. So this is going to be B dA dt over R. Now the area carved out by the loop is going to be the x-coordinate, which is changing as time goes on, times the length of the bar. So this is going to be BL over R dx dt. As you guys might expect, the derivative of position with respect to time will be velocity. So we get BLV over R. We are given all of those quantities. Go back to the first page for them if you want, but the length is 0.4, field is 0.5, resistance 0.3. Plug all of that in with your velocity, you get 1.67 amps. Calculate the magnitude of the net force. Again, this is Lorentz force law. So it's going to be equal to BIL. No sign phi here because the field and the current are perpendicular. Therefore, it's 0.5 Tesla times 1.67 amps times 0.4 for the length. So you're going to get 0.33 newtons, give or take some rounding, right? Hundredths place is always a good bet. All right, now here's the one that's a little bit tricky. Sketch a graph of the speed as a function of time. And I'm fairly confident for the first three intervals, but the last one I'm a little bit unsure of. And I'll try to physically justify it, right? First one is going to be an upside down parabola. And the reason why is because you have 1/2 mv squared is equal to 1/2 kx squared. So what you should expect is that because the spring is stretched out, compressed more at the beginning, you're going to get a higher acceleration at the beginning. And then it's going to level off just like in simple harmonic motion. And I apologize, it's not an upside down parabola, it's actually a sine graph, right? Because for simple harmonic motion, where a mass is attached to a spring, you get sine of omega t for the velocity if the spring is initially displaced. For T1, T2, it's going to be constant because there's no net force. For T2 to T3, you are going to actually get exponential decay. And the reason why you're going to get exponential decay is because of the induced current. The induced current is going to be related to the velocity, right? But therefore, that implies that the force itself, which is proportional to current, is also proportional to velocity, and it's pointed opposite direction as the velocity. And that might sound familiar from air resistance, linear air resistance, which we actually did get an exponential trend in as well. Now, because eventually the bars should slow down if this field kept going on forever, you would expect it to exponentially decay, not leveling off at some value, but just exponential decay. Now, if you go into the next part, you do actually end up with the same thing. You do actually end up with another exponential decay because as you go into the next field, which you should be able to actually see on the picture on the right half of my screen here, you should actually end up with another induced current pointing to the left, pointing clockwise this time. And in terms of that, that would also exert a net force to the left, opposite of your velocity. Similarly to with between T2, T3, that force should be proportional to current, which should be proportional to velocity as well. So I do believe that this is the correct graph. Again, if any of you disagree with me, let me know in the comments. But I'm feeling okay about that. I think that it is correct. Good. So moving on to part D, determine the total resistance if you have two in parallel. That's pretty easy, right? There are two resistors in parallel. 1 over Req is equal to 1 over R plus 1 over R. So therefore, the total resistance, right, which I called Req, but that's just going to equal R by 2. Good. In the original situation, right, you're given an acceleration. In this new scenario, what would happen, right? Are you going to have a lower or higher or equal acceleration to the original case? It has to be lower. It has to be a lower acceleration because you have lower current, right? The reason why you have lower current is because you were having a smaller change in flux as time goes on, right? Or actually, sorry, not that. The change in flux is the same. But what you are going to have is a if you have the same original rate of change in flux, right? You have a higher. Actually, sorry, what am I talking about? The resistance is lower in this case. If the resistance is lower, you should have a greater current. I don't know where I got lower current from. I apologize. I think I was thinking that total resistance is 2R when I was thinking about this, but no. It's a greater current because you have half the resistance and therefore twice the current originally at the beginning, right? So if you do have a greater current, in fact, twice as much, right? A greater current means greater net force by the same factor. Therefore, you have a greater acceleration. I apologize. I have no idea where lower current came from. I was thinking about that incorrectly. But it should be greater current. Good. All right. Now, part E, describe a modification that will result in a smaller induced potential difference. There are a couple of different answers here. The one that I would say in this case is I could say that you could decrease B. What that's going to do is that will lower the change in flux. If that lowers the change in flux, right, with respect to time, that will also lower the potential difference, which lowers potential difference. Good. Yeah, I'm feeling good about that. All right. Let's go ahead and move on to the very last question of this set. We'll go ahead and end the video off, and then we'll go ahead and move on to set 2 afterwards. All right, man. Trying to record all of these in one day is a little bit hectic, but I like solving these. So, all right, we are given finally our circuits question, right? RC circuit. 2 resistors, 2 capacitors, right? But do not solve a differential equation that could find charge on the positive plate of capacitor 1 when the switch is closed at position A. Differential equations in circuits always use Kirchhoff's loop rule. Sum of all voltages in a closed loop is 0. This tells us that E minus the voltage, the EMF in the battery, right? Minus I times R over 2. If you're wondering where I got R over 2, that's the equivalent resistance between 1 and 2. Same as in problem number 2. Minus Q over C is equal to 0. Well, I is equal to dq dt, so this implies that E minus dq dt times R over 2 is going minus Q over C is going to equal 0, and that is a differential equation. You could rearrange it if you want to. That should be fine. It has all of the terms that we need. Going on to the next part, it's asking us to plot charge density and power as functions of time. You would expect exponential rise, but leveling off for charge density, and you would expect exponential decay for power. And the reason why is because charge density is proportional to charge, and we do know that charge should be exponentially rising in an RC circuit when you're charging it. Meanwhile, power is proportional to current squared, and current, being the derivative of charge, is going to be proportional to e to the negative 2 over the time constant, right? So that's an exponential decay then. Good. Now moving on to part C, right? Part C is asking where the current is going to be flowing in the switch after you move the switch to position B. Should it be towards the left, towards the right, or no current? And I claim that the current should be toward the right. The reason why is that for capacitor 1, the upper plate is positively charged, and the lower is negative. So the current flows clockwise. Therefore, it should be to the right in the switch. Awesome. Determine an expression for the total charge of capacitor 2 a very long time after the switch has been moved. Well, there's one thing that should be equal on both capacitors after a very long time, and that is the potential difference between the plates. So I would say that B1 has to be equal to B2, but keep in mind that Q1 plus Q2 has to equal however much charge you have originally, because charge is conserved, which is Q0. So knowing that the voltage of a capacitor is equal to charge divided by capacitance, we get Q1 over C has to equal Q2 over 2C, which is the capacitance of capacitor 2. Therefore, it implies that Q2 has to equal Q1. So therefore, Q2 has to equal 2Q0 over 3, leaving Q1 as just Q over 3. If you're not sure exactly what it should be, you do have a system of equations you could solve. The one relating Q over C and Q2 over 2C, and Q1 plus Q1 plus Q2 is equal to Q0. That is a system of 2 equations you could solve. But it's proportional style reasoning that can help you out and save you a little bit of time here. All right, on to the next page. Good. So we've got just a couple more parts here. We're almost done with this question. On to the next part. Derive an expression for the total energy dissipated by the resistors from immediately after time t1 until new steady state. This requires us to know the initial energy stored as well as the final energy stored. And we know that the energy stored in a capacitor from our equation sheet is q squared over 2c. Well, only capacitor 1 has charge initially, and so that is going to end up being q naught squared over 2c, right? Not q naught, not q naught divided by 3 squared, because that's steady state charge. Originally, capacitor 1 just has q naught. The final potential energy is going to be the potential energy from 1 plus the potential energy of 2, which is going to be q naught squared over 9 divided by 2c, right, for capacitor 1, plus 4q naught squared divided by 9 over 4c for capacitor 2. And now we have to simplify stuff a little bit, right? Let's go ahead and factor out q naught squared over 9c for the time being. That's going to give us 1/2 plus 1, which is going to give us 3 q naught squared over 18c, or therefore q naught squared over 6c. Hopefully I didn't do my math incorrectly there. Now, the difference is going to be the energy dissipated. So ER, as it's called, ER is equal to UI minus UF. So that's going to give us, let's see, you got 3/6 minus 1/6, which is going to give you 2/6 or 1/3. So that's going to give you q naught squared over 3c. And that is going to be the energy dissipated by the two resistors, q naught squared over 3c. Good. While the switch is closed, if you move the separation distance to increase by a factor of 2 for capacitor 2, determine the ratio of the potential energies for each capacitor. Well, if you increase the distance by 2, you decrease the capacitance of C2 by 2 as well. So the capacitance of both capacitors ends up being the same. Well, if the capacitors are the same, if the capacitances are the same, the charges also have to be the same. Such that both have the same potential difference. Therefore, the ratio is 1. They have the same potential energy stored because they have the same charge, same potential difference, and same capacitance, right? U is equal to q squared over 2c. If q and c are the same, have to be the same. Good. All right, on to the last two parts, right? Derive expressions for the current from the battery immediately after the switch is closed and a long time after the switch is closed. Ooh, we're almost done here. a lot of switching these switches here. Well, immediately after the switch is closed, right, from position D, what we actually have for our Kirchhoff loop rule is that E minus I0 times R over 2 minus Q naught over 2 divided by C has to equal 0, because capacitor 1 is Q naught over 2. Now, here's the thing, right? We can't have E in our final answer, so we can't just try to solve this for I0. However, we should know that E is equal to Q naught over C, and the reason why that is because a very long time at the very beginning of the question, the capacitor had to have voltage equal to that of the battery voltage to prevent current from going to the resistors, and that voltage would have been Q naught over C then. So I can say that Q naught over C, right, is equal to the battery voltage, right? And in terms of thinking about this, right, there's a couple of things I've kind of been debating as to what the actual answer to this question is, right? But it's asking for the current from the battery and not the current through the resistor. So what I'm kind of, my reasoning behind my answer, which I'm going to put up on the screen in just a minute, is that the current from the battery isn't changing, right? The current through the actual loop is changing, because the capacitor is providing a current opposite of that of the battery. But when we're asked for current just from the battery by itself, my gut feeling is that that's just asking for exclusively from the battery and not the total current through the circuit. So what I could say is that the current from the battery at this point in time, right, would actually equal I naught would be E divided by the equivalent resistance, which is R over 2. And therefore, we should get that this would be 2Q naught over RC, which would actually also have to be the current from the battery at that same point in time as well, too, after a very long time after the switch is closed. That current from the battery would not be changing. Now, I'm not confident in that because I think a lot of it depends on what the question is actually asking. If it's asking for total current, what you would do is you would plug in Q naught over C for E, and then after that you could solve for I in the equation above, the loop rule that I wrote down. Right, and likewise, if it's asking for total current inside a very long time, the total current has to be zero, right? Because at that point, everything has reached steady state a very long time after the switch is closed. But again, the wording from the battery is making me think it's just supposed to be what is the battery itself providing, and I think that my work is correct for both of those. So again, let me know your thoughts about these questions in the comments. Hopefully this helped you guys out a little bit and made you feel a little bit more confident with your questions. Hopefully my reasoning made sense. If you guys have any questions as well, feel free to post those in the comments too. Next video, the final video for AP Physics C this year for the exams will be the FRQ set number 2s for electricity and magnetism. So I look forward to seeing you guys there. Thanks for watching and take care, guys.